Hello again, this is Timothy Baldridge, and today we're going to look at another function of the day. And today the function is going to be iterate. So, iterate. Let's take a look at this. It takes a function and an initial value. And we'll look into what this whole bit here means in just a little bit. Function and an initial value. So, let's say that we wanted to get a sequence of numbers, right? And we could do this with range. We could have range of 0 to 1000, and we could do a step of 2, right? And if we take 10 of these, we should see, how about we do that in a namespace here. There we go, 0, 2, 4, 6, 8, 10, so on and so forth. Another way we could actually do this is like this. We could have a function that takes a previous value and adds to the previous value 2, and then we could also start off at 0. And then we take 10 from that, and we get exactly the same thing. Now, so what iterate does is you give it an initial value, and it will return that value. And then the next item in the sequence is that value run through this function. And then the next one is that value run through this function again, and so on and so forth. So we could go here and turn this to 3, and now we have 0, 3, 9, 6, 12, so on and so forth. Now what's kind of interesting is that with range, you have to give range an upper bounds if you want to give it a step. You could do that like so. You could do long max value, and it's pretty much the same, but you know, this is a little bit weird to look at, I think. We can also simplify this a little bit by just doing partial of plus and 2, and there we go. But there's one of the, so what kind of brought this to mind, I thought this is interesting, is that someone on the mailing list showed how we could use iterate to solve this problem. But the question originally was, I guess Haskell has this primitive where if you do 4, 6, and then like ... it would return a list of 4, 6, 8, 10, so on and so forth, right? So I got thinking, maybe we could write a function that does that for us. So let's do defin inf list a and b. So we're going to take two values. So the first thing that we do is we find the difference between these two. So we do diff of b minus ba, so that's our difference. So if we look at our inf list for 6, we see now that here that the difference is 2, right? So then what we just do is we just do what we showed before and iterate partial plus diff each time starting with a. And we should now, if we do, we should see take 3 or 4 of these, we'll see 4, 6, 8, 10, right? And we can start this at 0 and let's say 3, and then we have 3, 6, 9. We could also do something like, you can do 6, so then our stride. So this is, it's pretty much the same as range, right? But it's automatically figuring out the stride for us given 2 examples. I mean, it's kind of a clever hack. I don't really know that this is something I've ever really needed. Hack is too strong of a word. It's a clever thing, right? I don't know how I would use it or if I would need it, but it's kind of cool nonetheless. So I think there was something else I wanted to say about this. But iterate does return an infinite sequence. It's going to keep on going forever and ever. And so you almost always need to put this take at the beginning of it. Oh, the other thing I wanted to try, though, too, is that this should work to go 3 and 1. And then what we have, and let's do a little bit, start at 10, and we're going to go to 8. So 10, 8, 6, 4, and we could even, crank this up to 10, and we start getting negative numbers, right? So that's kind of a cool function. Like I said, most of the time when I need this, I would just write range of 10 to 8 with -2 as the stride. Not to 8. We would do, long min value, like that. But I don't know. I don't know if one is actually objectively better than the other. It's a cool function. There are many other things though where this is useful. I've also used it to we can do this, something like this. So child. There has been times I've needed something like this: value 1, value 2, value 3, right? So we have this nested map. And it's compiled. Oh, no. So this one has no child, right? So now if we do something like iterate on D, our starting value is D, and each time we're iterating child, and then we say take while identity. So this is going to take until our value is nil. How about I do identity? There we go. We get all of the values here, and that's really hard to see, so let's do map value. There we go. So what we've done here is kind of walked. So we're iterating. First we're taking this outer structure, and then we're taking the first child and then the next child, and we continue. This will go on forever. If we don't have this identity, this will, you know, we can do take 4 here. If we take 4 off of this, we would start getting nils, right? This is never going to terminate. We just get a lot of nils. So if we do take while, then this terminates once we get a nil in there. And then what we have are a set of these hash maps, each item here, and we're just going to pull out the value. So I have used that a couple times. That's probably about the only time I've ever used iterate. But aside from that, it's kind of a cool feature. So one other thing we can look at about iterate is I was going to explain what this is. Well, in more recent versions of Clojure, if you remember the tutorials, I have tutorials on transducers. One of the things is that Clojure has this this thing known as IReduce. It's an interface that you can say, if you want to reduce over this thing, here's an efficient way to do it. So this iterate type actually extends async. It extends async, so it is a sequence, but it also includes, it's also an IReduce, right? So if we look at where we say reduce here, and we have a start, this code here is much more efficient. In fact, this code here has no allocations aside from whatever is allocated by this invoke function. So there's no allocations happening at all within here, as opposed to next here, which is generating the next item, right? So seeks do have this problem that each time you create a new cell, you have to create a new con cell or a new instance of this iterate seek. But a much more efficient way is to do this without any sort of allocations whatsoever, and that's what you see here in this reduce. This is just a loop, and we check each time to see if it is reduced, and we terminate when it is reduced. Otherwise we call the function with the next value. And so this here is going to get optimized by the JVM. In fact, anything down in this code may just be inlined right into the body of this function, depending on some things that are going on. So you're going to see this a lot. The other situation you're going to see this is actually with range. So if we let's take a look at our range here. Range does the same thing, and there's actually a lot of longs are used a lot with range. We use long integers, and so there's also an additional special case for range where we do all of this with unboxed integers. So here your start, step, and end are longs, as opposed to the normal version of range where start, step, and end are objects. So those could be, you know, doubles or whatever. But what this does here is it just detects that if everything is a long, then we can use this this enhanced version of range that could result in less allocations. And it'll result in less allocations because we're using these unboxed integers. We don't have to wrap them every time to stick them into an object. We do have to wrap them on the reduce. So if we go to reduce here, right here, we're going to wrap the long, but we'll only wrap it once. We won't be wrapping it whenever we do math. We won't be using boxed math. So anyway, that's about all I had for today. So that's iterate. You will see a lot of stuff in, I think repeat is another one. Let's see, is it repeatedly? Is that what I'm looking for? No, repeatedly is not the one. Repeat, it's just repeat. Yes, repeat is also optimized this way. And there may actually be some others that could be done in the future. Repeatedly perhaps could as well. But a lot of these main ones are already optimized to use reducible things. Now you may ask here, why are those written in Java, right? Why don't we write those in Clojure? The main reason is that if you look where we are at in the file here in Clojure core, this is like, we don't have anything that we could use to write these with yet. In order to write that, let's go back here. In order to write repeat, we need def type and we need a couple other things like, basically just def type. And unfortunately, def type isn't defined until way down here. So down here. So Clojure hasn't finished bootstrapping yet when we define repeat. And unfortunately, some functions like repeat and iterate and stuff are needed by macros that maybe eventually are used by def type. So there is kind of this chicken and egg problem. And so the decision was made when we wanted to add IReduce to these primitives, that the easiest way was just go write it in Java, get it done with, and don't try to do any sort of clever stuff with you redefining these after they're already defined or anything like that. So anyway, that's more than you probably ever wanted to know about iterate, but that's the tutorial we have for today. So thank you so much for watching.